My name is Shuai Bai from Harbin Institute of Technology, and my supervisor is Xinhong Guan. Today, my topic is exploring the potential of nanosilica to prevent early frost damage in Portland cement paste. And my topic divided into 5 parts: motivation, experiment, effect of nanosilica, effects of early frost damage. The last one is summary. First one is motivation. As we know, in the northwest, north, and northeast parts of China, covering more than 60% of land area, the average temperature in winter can reach minus 20 degree to minus 30 degree. In order to speed up the construction and put this project into use as soon as possible, concreting in cold weather is a common way to achieve this purpose. However, in so cold environments, concreting under construction may suffer from extreme weather such as the cold wave and snowstorms. As we know, since younger concrete is not fully hydrated, so the early structure is loose, brittle, and porous. So it results in poor strength and frost resistance. This figure is from Professor David. He used the low temperature SEM to observe the microstructure of cement during the freezing. We can see the figure A. The ice helps to support the structure in some way, but when ice is disappeared, the formation collapse like the figure B. So we can see the early frost damage affects the microstructure seriously, and it will further affect the micro performance. So as we know, nanosilica with high specific surface areas and activity has been regarded as an ideal material to improve the performance of cement-based building material. And also a number of researches has been carried out. We can see this page. Nanosilica can enhance the micro properties such as flexury strength, compressive strength, and feeder cell cycle. And it also improves the microstructure and accelerates the cement hydration like this. So considering the excellent performance of nanosilica in improving the property of cement paste of base material. So we want to use nanosilica to improve the microstructure and enhancing the resistance of early age frost damage. So these 2 points is our purpose. First one is this, and the second one is investigating the effect of early age frost damage on the microscope properties of Portland cement paste. Because we think only understanding the early age frost damage, the corresponding prompt measure can be carried out. We think this is critical for creating in winter. The next one is environmental design. This is the specification and information of nanosilica, and it is also characterized by XRD and SEM. This is the simple derivation. The water cement ratio is 0.35, and the contents are 0.6, 0.9, and 0.12. And for the cooling condition, the freezing temperature is minus 50 degree, and the initial cooling time is 25 hours for demolding. And the sample is divided into 2 groups. We can see this flow chart of cooling like this. The group 1 is the most simple, was stolen at minus 15 degree for 7 days, and then were killed at 20 degree for 28 days to carry out the testing. And the other one, we want to use this simple to simulate concrete under construction, explore the weather such as the cold wave or snowstorms. Another one is curing at the 20 degree. We can see this simple is without the process of freezing as the frost group foreigners group to explore the effect of early age frost damage on the cement paste. We're introducing our experimental, and we will show the result. The third one, effect of non-silica on the micro property and microstructure. The first is the micro property. The figure A is a compressive strength. We can see the 0.9% nanosilica can achieve maximum compressive strength like this. And similarly, we also see the migration coefficient was also decreased by 30.9% as the content of 0.9% like this. So we can see the 0.9% nanosilica addition is able to achieve the maximum improvement on the strength and the resistance of colloid ion penetration. Based on this result, we choose the cement paste with 0.9% nanosilica as the subsequent starting object, and we will call it as the freezing NS. This is the hydration degree. The TG and the DTG curves are shown in this figure, and we use this formulate to calculate the hydration degree. And we can see the hydration degree of simple with nanosilica. This one is slightly higher than the PC simple. But the calcium hydroxide content change a little. This is the post structure. The figure is a post size distribution, and in order to get a more detailed understanding of the PSD, so we divide the pollen into 4 ranges: gel pole, mesopole, and the capillary pole, and the lag pole. And like this figure, you can see it clearly. And we can see the addition of nanosilica increased the volume of gel pole, mesopoles, and capillary poles, and also decreased the lag points. In other words, the nanosilica achieved the pole refinement like this. This is the post structure parameter. According to the Professor Yan, the effector porosity and ink bottle porosity are defined by this figure, and the effector porosity directly affect the permeability of the cement paste. So we can see the addition of nanosilica decreased the value of effective pounds from the 7.2% to 5.2%, but only little change in the ink bottle points, like this. And we can also see the other post structure parameter are also decreased, like this table. And we can see the cycle pole diameter decreased up to 35.5, and totally porosity decreased by 10.8%. After that, we will going on the fourth part, the effect of early frost damage on the microstructure of cement paste. First, we investigate the strength development during the early frost freezing. We can see like this. In the first 4 days of freezing, compressive strength have slightly increased, and then compressive strength no longer increased. And the second one, and the compressive strength of non-silicon modified cement paste is slightly higher than that of the pure cement paste. And based on this result, we choose 1 day, 4 day, and 7 day to carry out the TG test. We can see this table is the degree of the hydration, and we can see the degree of the hydration of the nano-silica modified sample is also slightly higher than that of the reference sample. And we also see the degree of the hydration at the 4 day is similar to that at the 7 day, like this. So we can see the nano-silica accelerates the cement paste hydration, cement hydration, and we also see the cement hydration reaction stops after 4 days of freezing. This is the PSD of the freezing and non-freezing sample. We can see that the both simple post structure are affected by early frost damage, and we can see the pink value of freezing number is much lower than the non-freezing sample, and the most probable pole diameter is also increased, like this. So it means the early frost damage caused the deterioration of the pole structure, and we according to the pole size distribution, we further show the pole volume between the 20 and 300 nanometer. We can see this figure. We can see the small pole was decreased, and the larger poles is increased. That means the pole diameter causing, and we can also see the nano-silica reduce the larger points. That means the nano-silica repaired the pole structure. The next one is the hydration. We can see the degree of the hydration of the non-freezing and the freezing sample, and the chart of the hydration degree. We can see the early frost damage reduced the hydration degree, like this is 6.7, and we can also see the nano-silica compensate for this loss. The change just the 0.7, and we also use this formula to evaluate the pozzolanic reactivity of the nano-silica. Use this formulation, and we can see the post-land activity of nanosilicon in the cement city is weakened like this. Okay, this page is the CSH gel. We can see the wave number is changed from the 961 to 957. So we can see the early frost damage affected the CSH gel structure. Of course, we are still studying this part, so we don't show more detail. The last one is summary like this, because the time is wrong. So this is the summary. My presentation. Thank you for listening. That's all. Thanks.